Hello and welcome to the KIM-1 Resurrection Series, episode 12. In the last episode we cured quite a few of the crashing bugs, but there still seems to be a major one that's taking it out, and I shall hopefully resolve it in this issue. I'm recording these as I'm going along, so could be all sorts of bits going on. Let's reset it so it's running, and let's take a reading, see what we got. So we're running on just the replacement RAM board, and all the ROM and I/O is being provided by the RRIOT clone chip now. Let's see what we got on that. And here we go, this is running normally. Here's going through the displays and the keyboard read, and we've crashed already. So let's go back and grab that again. Okay, reload that and oh god. No. That's not good, is it? Press the reset. Okay, it's up and running again. What I'll attempt to do now is I've got channel 31 connected to A15, and often when it crashes it tries to read further up the memory. So if we put on a pre-trigger, if it tries to read in the top half of memory, it will trigger and it will grab the data. So sometimes that happens shortly after you've had a crash, and that's how I managed to see what's going on just before it crashes. So we're scanning at the moment and just waiting for it to fall over. I'm sitting there, it's running okay at the moment. Oh, there it goes. Did we get anything? Yep, it grabbed it. There we go. Caught something. Let's see what it's caught. And oh, there we go. It was running okay. And it just happened to catch it right near the end. Hopefully we've got enough data. So it was updating display 4 when we suddenly got, well, with 31 when this triggered here. When it tried to run something in high memory or access it. Which you should never do on normal running. So here we go. I think this is probably where it fell over. This code is all familiar. So I'll bring up the actual software listing up. There we go. Let's bring it over here and put it into monospaced. You can see it better. And right, where are we looking for? We're looking for 1F5C. Oh, here we go. In that delay loop that's going round and round for 500 cycles. This is the most likely place to catch it because it runs this code a lot. We've got 1F5C's D0, white branch is not equal to FD. That is just a preload, we don't need that. So we jump to 1F5B because this is a backwards branch. Oops. Come back. So we're jumping back to here, 1F5B, which is 88, which we got here. 1F5C is the next one, which is D0. Loads in a D0, so that would have been, so the address would have gone out here. Data would have come on here, so it comes on quite quickly now. Strobed in at this point here. So that's where we're going to start the instruction for branches not equal. And here you see it's 2 cycles long. So at this point here, oops, what's the code? This point here we should be doing 2 cycles for that instruction. Should end in there. And now we've got 1F5D, 1FC, that should have FD. So at this point here we should have FD coming out onto the bus to be strobed in. And we just got D0 again, which is branch if not equal again. So it's going to try and branch to that location because it's going to read that in instead of FD. So what address do we get? We get 1F2E. So it jumps to 1F2E, which it shouldn't have done. 1F2E jumps up here. It should get a 4A come out, which it doesn't. It just gets DO. So it's getting somewhat confused around here. Why is the data bus freezing? This is going to take a bit of thinking. This is the code that's actually running. And you notice here, this bit where it sets the port A to read has been turned off. But then again, further down here, I've also taken out these tests for the reset. So it won't be going back, doing a reset. Or even there, I'll take them all out. So the only time it goes through this code here is when it first starts up, clears the RAM, that runs through here, jumps to this point here, and then carries on from there. So it should never change the bus. And if you do a read for the ROM, it would come through here and go to the ROM read bit. One of the first things it does is turn it all on. There, actually turns data port to output, enables the buffer chip, puts the data in, and then turns the outputs on. Bang, puts the data on the bus. But it's not doing that. What I've done here is, this is the normal KIM-1 ROM. Yeah, I'll just rename that as old, ROM code old. And here there's, is normally named as Test Rom code. Just renamed that ROM code. And in here is a little sequence that goes round and round. Let's see if I can find it. Here we go. It's this code here. Used this before to test the memory. So it just comes in the same place as the KIM-ROM normally comes in. And this is just loading FF and AA in and out of data all the time. This is basically like a RAM test. And tell which bits are on or off. I'm just using a bit of code just as a piece of code to run. And we'll have that running instead of the actual KIM program to see if it's anything to do with the software. So I'll compile all this and programming it in, and seeing as it just looks to find where the ROM code is, whereas I've got a pointer in here somewhere that actually points to the ROM code, just feeds that out instead. So we compile that, load it in, and see what we get. Back on the board here, all loaded in, running. Let's reset button. We won't get a display or anything, but we can check what's going on by looking at the analyzer. Whoops, wrong button. Where are we? Oh, we're over there. There's the analyzer box. So if we trigger that now, can't use the pre-trigger until we've got something we can trigger off. We'll just bring that in, and if we look at that, reload that. There we go. We can see the addresses building up, cycling round as we're just putting data in and out. So, and if you zoom in, there's the actual code running there. Similar sort of addresses. And we just have to keep resampling until we crash to see what we got. Oh, there we go. We've crashed already. But this is, there's the phase 2 clock. We have got absolutely nothing happening. Ooh. So that proves it's got nothing to do with what bit of code it's running. It's some sort of hardware issue. Well, I say hardware. I think it's something to do with either the right clone chip or maybe the socket it's plugged into. Right, I've put this wire link, you may see just here, this orange one. That goes on to one of the inputs on Logic Analyzer. If we look at the actual circuit for that, if we zoom in a bit, it's this one here, RF1, and that comes down here onto the buffer chip. Now this is the data going out from the RRIOT chip onto the data bus, and it's got an output enable. I mean, read write here tells you if you go in or out. That's controlled by the 6502. Then this output enable here, so we can turn this to tri-state if necessary, is controlled by the microcontroller out of port RF1. So it pulls that down to 0. This then is active whether it's in or out. And on the actual circuit board, that's this there's a resistor just here, and then this pad here actually goes through to the pin down here for doing it. So I've tacked a wire just on there, and I fed that across to the analyzer, because if you actually look in the software, when we're coming to read the ROM, so if we look at in the software, the ROM code here, bit clear latch F1, so that's that output. It sets it to 0, and that enables the input or output IC on the bus. Now, just ran it, and it crashed. And here we've got, this is where we get the crash where the data bus sticks. And this one at the bottom is just the trigger that caused it to happen, and the pre-trigger. This one here is the phase 2 clock switching on and off. And this one here on 29 is that enable signal. So every time it comes low, it enables the data to go out onto the data bus. Then it goes high again, then goes low at this point here, so the data's getting put out. High again here, goes low, the data gets put out. So we've got FD has been put out just here when we're at that address, which is correct. But then it just stays in that condition all the time until we get to here. And it does it again here. It's not going on and off as you expect. As it's running back here, you expect it to be going on and off pretty steadily. But it stops. So obviously the RRIOT chip is not calling that bit of code to turn the output on. It's not calling any bit of code to turn that output on. So the bus sticking must be internal to the RRIOT chip. Something in the software. So we've got this bit here where it turns it on. If we go further down, when you're doing a reading, say the RAM, it will be turning it on as well. It's further back up here. When we're doing the check what's going to go on and off, the RAM comes through here. There it is. It turns the data bus on there. And that's for that. And the ROM one is actually in the bit of ROM code for turning it on. So whatever is doing a read or write, it should be turning that on, and it stops doing it. So this is not getting called. The K7 bit's not getting called. Or the K5 bit's not getting called, which means this is just looping around and around. It's not seeing the chip select. So we'll attack that bit next. I found the smallest enamel copper wire I've got, which is 0.1mm in diameter. And amazingly, on my first try, I managed to get it to solder onto port G wave 6. That's on pin 1, 2, 3, 4. Then the other end I managed to scrape clear and tin a bit so I could connect it to the logic analyzer. So now I could turn an output on and off to sample what's going on within the processor. Well, that small wire I connected to port G pin 6 is in here. I'll set it on there. Now this is the startup code. It sets everything up, etc. Set it there, so it's on. Then does a few other bits and pieces. And then we get to this point here, the very last bit before we actually start running the program, I clear it. And then we come into the main sequence just here. And we start running the code, which always loops back here, backwards and forwards through here. Now the only way that port G pin 6 would ever get turned on is if the processor resets. If we have a look at this, this is the crash we just had. We zoom into the crash. You're just here where the bus jammed. This bit here, this is turning the tri-state data buffer on and off. You notice it stays on, and that's when the data bus sort of just sticks where it is. Well, if we look a bit further along, you can see this signal here is that port G bit 6 comes on there, and close it up a bit, or quite a bit, comes on here, and off there, and everything starts processing again, but at the wrong addresses. So this is the RRIOT chip clone resetting. And that's why it's been such a pig to find. Actual processors crashing and rebooting and starting up again. Something wrong with the chip. But that's why we're getting such random crashes and everything's just jamming on, because the actual PIC processor is stopping. Here's the reset system built into the microcontroller. We've got a reset instruction that can reset the processor. Master clear reset, which is used when programming. There's this watchdog module, so you have to keep resetting that if it's watching. Then there's one that measures the supply, so you've got a brownout detection and power off detection. Then there's all these other internal things that can trigger it as well, like bad addressing mode, etc. Well, if there is a reset caused by one of these, the data is put into a register. So what you can do is, in the code, in this part here, you can read this register called archon. So what I'll do is I'll take the value in there and I'll place it into the bottom of the 64 bytes of RAM on the right too, so that when the computer's running, we can actually look to see what was in there. And if the RRIOT chip crashes, then you have to press the reset on the KIM to get it going again. That resets the KIM, but it doesn't reset the RRIOT chip anymore, because I took that bit of code out. And you should be able to see, by looking at this location, what actually caused the reset. Well, when we first start up, we have a number 7 in there, which is the power on and brown out, which you always get when you first start up. Well, that's okay, but it never changed whenever it crashed. So does that mean that none of these things here were causing the reset? Well, I puzzled over that, and I decided, I know what I'll do. I'll have a look at the configuration. So we come over here and look at the configuration. We've got all these bits you have to set here. There's a load of bits you have to configure on the microcontroller before you can program it, to tell it things like what clock to use to start up and various bits and pieces. I had all the watchdog and everything turned off, but I stumbled across here. There's the brownout turned off. I stumbled across this one down here, which is DMT enabled, and that was enabled. And that's a Deadman Timer. And I thought, what's that? Is that something to do with the resetting? If you go back over here, see if I can jump to the page. There's this Deadman Timer, so part of it. And it will count. If there is no instructions going on, it will make this happen here. You'll have the counter here going on. If the instruction stops going for any reason, it causes this Deadman Timer event, which causes a reset. Well, there's nothing about this in the reset circuitry. So, you know, it's not a watchdog either. They talk about making RAM radio circles to find things. So I turned this bit here that said enable in the configuration to disable. Recompiled the code, and it all works. It doesn't crash anymore. So it's a wonderful hidden feature of microchip again. I don't know why I use their chips. I just bang my head against the wall so often with them. So, this bit of code here is no longer needed. Okay, it's time to replace the RAM chips. These two down here, they're the dead ones. I replace them. That's a lot brighter in real life. The camera doesn't seem to be picking up very well. Well, that's everything done and running, apart from this 6.2 volt Zener. I've got to get hold of one. I thought it was a 5.2. I've got a 5.2 here ready to go. But then I saw it in the Sega diagrams being 6.2. I'll have to find one of them, but that's the last little bit to do. That's just soldering in a component. But there we go. It's all working. So if you want to see what else I'll do with this board, don't forget to like and subscribe. And you'll be able to follow future projects with the KIM-1.